Very nice to see you all. Turn out here, nice turn in line as well. So it's all very good. So we kind of just stuck this extra seminar in because Despina here is just visiting us. Just before she gets into her stuff, I just thought I'd briefly explain why you're here really, and kind of my involvement and what's going on. So yes, Despina is a scientific software engineer with RAL Space, but also kind of working in a lot of the sort of data analysis and kind of visualizations as well.
Yeah.
Come on in, come on in. A lot of visualizations and data processing and things like that. She's also just working with the team that I've been doing work with, who's actually on environmental testing. So this is the cheesy photo here. What do you think is inside the large array of loudspeakers? I think most of you know the answer to this question because I've probably talked about it before. That would be a spacecraft. Why are we doing this sort of thing? Hello, come in. Because rocket launches are insanely loud, aside probably from volcanoes. They're pretty much about the loudest thing you're likely to come across, really actually extremely challenging to measure. One of the kind of cliches about this is if you actually work out the pressure amplitudes that are going on in terms of the dB levels people quote to you, you actually work out that the atmospheric pressure basically gets nullified, and technically speaking, the acoustic wave is bigger than the atmospheric pressure, which obviously can't actually happen. There's some other things going on, not least a whole load of other pressure lifting up a rocket. But some of these numbers are crazily large, and you need to make sure that spacecraft can actually sustain this. And there's various different types of tests. Go back to the Apollo era. Some of the original capsules they actually built kind of almost a bit like impedance tubes running down the side of the spacecraft, kind of firing incredibly high intensity sound down the side. They don't really seem to do that so much anymore, but people are very concerned about noise and its effect on satellites and very sensitive equipment on satellites. I think you're going to tell us about some of the fantastic instruments that RAL develop, and they can, you're often trying to fight to get weight as low as possible. And that makes things acoustically susceptible. And they do a lot of vibration isolation, but the thing about the noise is you can't actually really get rid of the noise. It's always going to be there bouncing around. And to try and save weight inside the fairing would make things too heavy. So basically, things need to be able to survive a loud environment. And traditionally, they've used reverberation chambers like this. Is our reverberation chamber downstairs, the larger one. This is the one at ESTEC in the Netherlands, the large European acoustic facility, which is 11 meters by 9 meters by 16 meters high and can hit 154 dB. These big horns down here on the left-hand side are about the size of a person, and they're driven by enormous compressed gas modulators. So they literally pulse high pressure nitrogen through them and create noise that way. And that works very well, but it's very expensive and very inconvenient, and you have to take the satellite to the test facility, which might not be convenient. So another alternative is to kind of bring a portable sound system, like a big PA system, to the test article. In this case, that's the Orion capsule. These are photographs from an American company called MSID-FAT. There is also the European service module from Artemis. Also being tested by enormous arrays of loudspeakers, and this is actually quite nice because this stuff has actually flown to the other side of the moon. So there it is on the far side of the moon. So this has something happening for real. And there was actually a serious problem with this where they did these tests, and they did actually find quite severe acoustic susceptibility in the solar panels on this. Actually, they had to do some corrective engineering, I believe, because the solar panels on this were too susceptible to launch noise. So I've been doing some consulting on this. So down where Despina's working, down in Harwell in Oxfordshire, we've got the new National Satellite Test Facility down there, I was involved in doing some reviews on some of this work, and then the procurement of these large loudspeakers that are all about the size of a Ford Fiesta, and we'll do something like about 100, I think about 148 dB each or something like that. Some crazy volume. There's a lot of transducers packed inside that box. As to why Despina's here this week, Ian, who's in that photo there at RAL, wants to do some measurements, just testing, and some research, just testing, is this system performing as well as they want it to? And I've been advising him on just putting some microphone arrays together. And this week, by chance, Finn here has been doing some stuff for his student project, where we've been doing a kind of scale model version of this. So we've got a little microphone array there, little microphones on a stick. And then we've got a whole load of speakers that some of you might recognize have been salvaged from the wave field synthesis, which basically means we can simulate one of the DFAN tests, but small, and kind of remap all the sound drives and things like that. There's a little micro array. Here's, is this going to work? It's probably blast everybody with noise here. What's going on with this stupid mouse? I don't know how loud this will be. This was quite loud before. Let me turn it down a bit. So just firing lots of noise at things, really, you know, lots of speakers, and then play the most boring signal you can imagine. There we go. So that's that, and Despina's working on getting some software developed for RAL that will just do the same sort of measurements that myself and Finn have been doing. So that's what she's here. So there you go. A bit of a long-winded preamble, but that's why. So I'd like to introduce you now, hand over now, and thank you very much.
Thank you so much for the introduction. I hope you guys can hear me. I hope I'm not too quiet. So yeah, I titled this Life at STFC, but it's more like here's everything I do at STFC, because I'm involved in a lot of projects lately. And one side note is that at times it will talk a lot about me, but it's because I'm using some of the slides that I used at ESTEC when I was trying to get them to hire me. So that's the reason. So a little bit about me. I'm a computer science student at Newcastle University. I'm currently doing my industrial placement at ICE's new neutron source as a scientific software engineer, and I'm working part-time for RAL Space. And I've worked for JP Morgan, Palantir, and Amazon in the past. And yeah, at university I host a lot of lectures on Python, so that's mainly what I do. So right now at ICES, I forgot to explain something in the previous slide. Okay, so yeah, I wanted to explain a little bit about ICES here. So can you see my mouse? No? Okay. Sorry.
Right, no, that's just stupid mouse.
Okay, cool. So perfect. So yeah, this is a diagram of our synchrotron at ICES. So yeah, there's a linear accelerator here, which accelerates particles which go into the synchrotron, which get accelerated to 84% the speed of light. And then we have two test facilities, so TS1 and TS2. TS2 is way newer, so it has a few less instruments, but they're much more efficient than the old ones. Yeah, so they get accelerated. They come to one of the target stations, and here's where the neutron scattering happens into the different instruments, with which do different tasks, which I'm going to go into later. And yeah, so we do muons and neutrons, and muons get converted because we use protons to accelerate. So muons get converted right at the end because they have a very short lifespan, about 2.2 microseconds. So yeah, and what this thing I'm working on is called MANTID. It's meant for data manipulation, analysis, and computer vision for the data collected by ICES. So the instruments do spectroscopy, diffraction, reflectometry, chip irradiation, and imaging. And that's basically what our software helps support. And it's a collaboration between mainly the UK and Oakridge in the US. So we work very closely with them. Here are some photos from ISIS. This is the center of the synchrotron. So just a bunch of analog data acquisition systems, which we're switching to digital quite soon, even though analog systems are preferred usually because they're much more reliable, but no one makes them anymore. So unfortunately, we have to switch. And yeah, here is the synchrotron and the large magnets that concentrate the particles along the way. And these are the different instruments here. They're different color each, so you can tell them apart. So some of the things that I made, this is an algorithm for Mansit, which is called Create Monte Carlo Workspace. Not the most creative name, but that's literally what it does. This is just a snippet of it. So it's written in C++, and it uses multiple threads so that it runs faster than normal. And basically what it does is we have a lot of random noise generation functions for fitting, but we have no way of testing them. So this is what this does. So it samples from a workspace from the probability distribution of the input data. And then I use cumulative distribution function to test the fitting functions and modeling. So yeah, this is what it looks like when it works. Another thing that I'm working on right now, it's called Mansit Imaging. Even though it's the same name, it's a completely different software. And this is for neutron imaging for tomographic data. So this is the instrument that this software is used for. It's called IMAT, and you place an object on this little disk right here. And basically the beam is it's like the largest area of any instrument when it comes to the beam, because usually it's very concentrated, but it's quite big to capture the whole surface area of the object. And using this little black box, which has a camera in it, we can take photos of the sample using N-rays. So our software basically makes the images clearer. So for example, it removes outliers here and gives you a clearer image. Or there's like different ways to view the data and stuff like that. Yeah. So here's a brief overview about tomography. So if you say that this is the sample right here, yeah, the yellow star is the sample, and then the box here is a detector. And using this, the sample is in the red box, and we can rotate it. And if we take photos of it at multiple angles, then we can take a 3D image or a map of the sample. And N-rays are very useful because they're very sensitive to different materials like lithium. So it's very useful for testing batteries as opposed to X-rays. So for example, here, this is something that we use to reconstruct images. It's called the Beer-Lambert law. And it's like if you think about it like shining a flashlight, which is the X-ray source, through an object and measuring how dim the light gets on the other side, the law says that the dimming depends on how much material absorbs the beam along its path. So what we're doing is we're comparing the detected intensity to the original intensity. And the difference tells us the total attenuation. So if you collect these measurements from many angles, then you can piece together a 3D map of how the object absorbs X-rays or N-rays. So yeah, if you do the minus log of that law, then you can invert the colors and you can see the object much clearer. So yeah, another thing I'm working on is called flat fielding, and it's basically another way to clean out data. And yeah, so you need 3 different images to clean out the data using flat fielding. The raw image, which is just the object with the beam on, the object, a photo with the beam off and without the sample, and then a photo of the beam on without the sample. And then you do this calculation right here, and you can have this corrected image from the raw image. So that was for ISIS, very brief. And then, so I'm going to talk about a bit about space in the UK. I don't know how much you know about that, but I'm just going to start with this. So this is Harwell campus where I work. So we have the Diamond Light Source, which is the largest particle accelerator in the UK, and it mainly does X-rays. We have the Central Laser Facility, which used to have the largest laser in the world, but like the most powerful one, but that has been that's outdated. But we're building a new one called Vulcan 2020, and the ISIS neutron source, which I just explained, and the European Space Agency's communication center. Yeah, and there's 6,000 people that work here, and it's a billion-dollar campus. It's very cool. It has lots of things going on, and also we have a lot of startups and companies that are in the space industry that work that are in the campus. So it is basically a space cluster full of great and new ideas about the space industry. So yeah, and also we have a lot of spaceports in the UK, and we're also launching our first rocket, which is directed by a company called Orbex, and I think it's going to be in January of this year. So yeah, we're gonna launch our first rocket from the UK. And yeah, this is RAL Space. So yeah, it holds the National Laboratory for Understanding Space and our environment. So yeah, this is an overview of spacecraft testing. So there are basically when a rocket goes to space, as you know, it's kind of hard to fix it if something goes wrong. So we need to ensure that everything goes well. So there's 7 stages to testing. So we have antenna measurement system, electromagnetic compatibility, thermal vacuum test, center of gravity, and moments of inertia, pyroshock, acoustic test, and vibration testing. As far as I'm aware, we can do most, like, except from pyroshock. Oh no, we can do that as well. We can do all of them, RAL Space. So when people send their satellites, usually they can get tested here. And because, for example, the National Satellite Test Facility has very modern facilities. A lot of them are better than ESTEC in the Netherlands, so a lot of new satellites are actually going to get tested here. So yeah, this is RAL Space. So as John mentioned earlier, I'm working on microphone calibration for DFAN, and I'm developing this code that I call Amplify, which for calibrating our microphones. So this is some people testing an antenna, which was the first step of testing, as mentioned earlier. And these are some of the DFAN microphones, and the shaker is right here, but you can't really see it. And this is a large vacuum chamber. Yeah, so this is DFAN, as mentioned earlier. You guys probably know what this is, but this is not NSTF's DFAN. I just couldn't find proper photos because usually when there's DFAN tests going on, you can't take your phone in with you. So
that was the demonstration of one of the American companies.
yes,
Actually, the one that didn't win the tender. So
yeah,
yeah.
yeah. So yeah, this is an example of DFAN. This is the only photo I had, was a video. So yeah, these are our microphones. You actually had a better photo of this. And yeah, this is me doing satellite. So yeah, something else me and my colleague did this year after I started my placement is we wrote a paper about a conceptual satellite about detecting debris in space that's less than 10 centimeters in diameter because it's really hard to detect. And we have no mapping of it whatsoever. So we came up with an idea and we presented it at the largest small satellite conference in the world. And we won first prize. And that's why I got my place at RAL Space. Because usually when you have a placement at RAL, you can't really change teams, but I'm just doing everything. Other conferences that are going on site, which if you guys ever visit, feel free to join. There's conferences almost every week. We have like conferences at ESA, like Small Vehicles Symposium, and the head of Goddard Space Flight Center came and gave a talk, and the head of science at NASA. So yeah, we have a lot of cool conferences and a lot of outreach events, like for example, stargazing event, which are usually for younger audience. So if you guys have kids, can bring them. It's usually free. So yeah, it's just other stuff that I did. And now I'm about to embark on a different internship with the European Space Agency at ESTEC in the Netherlands to study the sun. So I will be implementing a lot of machine learning methodologies to predict solar flares using data from the HINODE instrument. And yeah, hopefully that goes well. Yeah, and I'm really excited for it. Also, these images are taken by RAL Space's instruments. So yeah. I won't talk about the rest of the stuff because I don't have for it right now. So yeah, that's all I have to say. Yeah.